Hello grade 12s. I'm going to show you now how to derive a formula to find the present value of an annuity. So let's give it this heading here, the present value of an annuity. And I'm going to use a very similar, the same approach that I used in the previous video, except I'm going to make it more general. So I'm going to consider a timeline, and on this timeline we'll have n time periods. So we've made that general, so you can imagine that's the one before that will just be Tn minus 1, then Tn minus 2. So, for example, here, the end of the first time period will be over here. Now what I'm going to say is that there's a payment that's made at that point, and then a payment of the same size is made over there. So we can imagine this will just continue along. And so these payments that are being made over time are the same value, and this is what we call the annuity. Now, there are payments in between here. I'm just leaving them out for now because they seem obvious. So the question then becomes, how do we find the sum of all of these, but in terms of their present value? So basically, I want to take the first one, I want to present value that back to the present day, which is T0, and then I want to present value the next one, and I want to add that all up, because that's going to give me the present value of the annuity. So I have to do it for each one of these payments of x. So let's start by actually writing down that idea. So we'll say it's the sum, and you'll be familiar with the SN notation from sequences and series. And the very first payment into this annuity is going to be x, but is that the present value? No. In fact, to find a present value, we're going to use something called the present value formula, which has a couple of ways of being written, but for our purposes I'm just going to call it like that. And that's a minus n there in the corner. So, how do I find the present value of that first payment of x, which is over here? I'm simply going to go 1 plus I to the minus 1, because there's one period of time that's going back. Now what's the next one going to be? Well, the next payment, which is made at the end of the second year, needs to go back in time 2 periods. And so when I use the present value formula for this one, I'm going to get that amount. You can imagine this process could continue in the same fashion, with the next one being x times 1 plus I to the power of minus 3. Now I'm going to skip to the end, because the end is probably the more interesting part. So I'll leave a little space here and I'll go, well, look at that last payment which is being made at time Tn. How many time periods does it need to journey back in time? So it's also going to have this initial structure, and you can imagine, well, if it starts here and it goes 1, 2, how many time periods to get back to T0 does it need to go? Now if you think about it, that's the nth time period, so it needs to go back in time n number of times. So that one is going to look like that, x times 1 plus I to the minus n. It's minus n because we don't know what n is when we started this. Okay, now, if we want to sum up all these payments which are being present valued, we need to think about, well, what tool do we need to use? And we also need to recognize something. This is in fact a geometric series. And it's a geometric series because it has a first term, and that very first term we often call A is just going to be x times 1 plus I to the minus 1. Then we need to look at the R value. Now, it may not seem obvious, well, it will seem fairly obvious in terms of the minus 1, minus 2, but what do I need to multiply term 1 by to get term 2? And if you think about it, and you can even do the test by taking term 2 divided by term 1, but all I need to do is multiply the first term by, or not x, it's going to just be, let's cross that out there, it's going to be r must be equal to 1 plus I to the minus 1. So think about it, if you multiply the first term by that, you get x times 1 plus I to the minus 2. If you're confused by that, stop the video and just take a moment to consider it, because this is really, really important, why r is 1 plus I to the minus 1. Okay, so now, once we've done that, we can actually use the formula that we've learned about before for summing up a geometric series. So that is going to be Sn is a r to the n minus 1 over r minus 1. And now what I'm going to do is I'm going to substitute in the values that I know already. So what's a? Well, a is just going to be the thing above here, which is x 1 plus I to the minus 1. Now it's going to look complicated because there's so many brackets, but essentially all I'm doing is substitution. So I'm leaving a big bracket open there, and the next thing I want to do is I want to put r in brackets. And r, we've realized, is 1 plus I to the minus 1. Now that's r. Inside of that, that needs to be the power of n. I've got a minus 1. And then over all that, we need to think about what's at the bottom normally. Well, it's another r. It's 1 plus I to the minus 1, and then minus 1. Now, this looks like an absolute mouthful, and I'm going to go quite quickly through this bit. This is not an examinable proof, but it's nice to know how we get our neat and fantastic formula at the end that we're going to use most of the year, because it basically is a whole bunch of algebra that neatens this up. Okay, so if we're going to neaten this up, like I said, this isn't examinable, but it's nice to know. So what I'm going to do is that first bit, using the laws of exponents, I'm going to write that as that. Okay, now think about why if it becomes below the line it becomes a positive 1. Then in terms of my bracket here, what I'm going to do is inside this bracket I'm going to get 1 plus I, and the interaction between this minus 1 and n is going to give me a minus n. And then this is going to stay like that as a minus 1 on the bottom there. And then over the main denominator, what I'm going to do is, again, I'm going to do the same trick. I'm going to bring this below the line. This is going to become 1 over 1 plus I, and it's now to the power of positive 1, which we don't need to write, minus 1. Take a moment to convince yourself of that. Okay, so now what I'm going to do is, I'm going to multiply the top and bottom by the following. Times the top and bottom by 1 plus I. Now, 1 plus I over 1 plus I is actually 1, so it doesn't change the overall value, but it neatens up this expression greatly. So, the effect that it's going to have on the front part is it's going to cancel out this denominator at the bottom here, and so that's going to disappear. So on the next line what you're going to see is you're going to see just a plain old x in front, because it gets cancelled out, and then inside here, inside the bracket, we're still going to have 1 plus I to the minus n, minus 1. Now on the bottom, stuff also gets cancelled out, and what we see is that the 1 plus I goes to the first bit over here and creates 1 plus I over 1 plus I, which actually gives us 1. But then the minus 1 over here needs to be multiplied by 1 plus I as well. So we get that. We're almost there. So then, if we move that up a little bit, what we're going to see next is that if we apply this minus into the bracket, you're going to see that becomes a minus 1 and that becomes a minus I. And so now on the bottom we have minus I. And then on the top what we're going to have is we're going to have this. Same as what we had before. And then the last step, what we're going to do is we are going to multiply both the top and the bottom by minus 1. And if we do that, this thing on the bottom will become a positive I, and on the top the x is actually, okay, so we're going to multiply the top by the negative, but we're going to bring the negative into the bracket, and what happens is the negative 1 at the end here, because it's being multiplied by a negative, it's going to become a positive, and so we're going to get a positive 1 in our formula, and the second bit is going to become 1 plus I to the minus n. So think about that, why that happens. If you multiply the top and bottom by a negative, it almost allows us to do a switch around. Well, it does allow us to do a switch around. Okay, then the very last step. We said this was a summing up of the present values. We tend to label this on the formula sheet. We just say present value instead of SN. There's the present value. And then the actual formula, to neaten it up, instead of having two sets of circular brackets inside each other, we just have the X. We then have one big square bracket, 1 minus, then the circular brackets to the minus n, and we close the square bracket, and that's all over I. So this is the formula for finding the present value of a series of payments over time, or the present value of an annuity, given the assumption that the first payment is made at the end of the first period and the last payment is made at the end of the last period. And except for a couple of cases, this formula will work for pretty much everything that we need to deal with, and those few cases like missed payments and things like that, we can just modify this formula. Now, we do not need to know the derivation, but it is nice to know the maths that it stands on, and it also helps us to understand why it works like it does. Alright.